Okay, question 10. I really hope you get a question like this on your main GCSE exam because I think you're fabulous at it. So let's have a quick look at this. Stars may originate as a nebula. Describe the process that occurs to produce the conditions necessary for nuclear fusion. So we're going to say that a nebula is a collection. I'm going to just use letters now. Is a collection of dust and gas. It has an unequal distribution. In this area, so this means you can use a diagram if you wanted. In one area, there is increased density, so increased gravity. Next part, so work is done by gravity to pull the dust and gas into that area. This compresses the gas. This increases the kinetic energy stores. Okay, in effect what we're doing is we're transferring gravitational potential energy to kinetic energy. This leads to temperature increasing and pressure increasing, and once we reach a critical value for this, fusion starts. And I know I've done that really quick, but I'm very confident that you're pretty happy with that. Okay, next one. So we've got Einstein's equation equals mc squared. Calculate the loss in mass. So I've got to rearrange this. So I need to get m on its own. So that c squared is going to have to go underneath the e. So m equals e divided by c squared. That's going to equal 3.86 times 10 to the 26 divided by 3.00 times 10 to the 8 and squared. That's the bit that you'll miss. The other bit is this is going to take a bit of calculator practice. Remember to put brackets in your calculator around the squared. Don't, if you see that in your calculator, 3 times 10 to the 82, you know you've done it wrong. So just make sure you use your calculator well. Shove that all in, and that comes to bear with me, 3.86 times 10 to the 26 divided by, open a bracket, 3. Oops, already. And make sure you use your arrow buttons properly. I almost made that mistake then. Bracket 3.00. I'll just use 3 times 10 to the 8. Press my arrow button so that I can put my bracket in. Squared. It's brought up syntax error. Do it again. 3.86 times 10 to the 26. Arrow. Divide by 3. Oh, sorry, open a bracket. Actually, this is blinking fiddly. 3 times 10 to the 8, arrow, bracket, squared. Please give me a number this time. Oh, my calculator's having a fit on me. Don't worry, this time I'm going to cry. Yay! Right, what have I got? 4, 2, 8, 8, and the other 8s. 5 and then a 9. Okay, right, so the next thing is I've got to go to the right number of significant figures. So what I'm going to check now, this is helping me know those number of significant figures. So I can now say I've got 4.29. So round up on that one, and then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9 kilograms. There we go. Oh, and this is lovely. Okay, so this one we've just done. So we've got to Big Bang, origin of the universe, explain how the evidence supports that the universe is expanding. So that's going to be all about redshift. And the universe began at a single point. We're going to relate to redshift, and we're going to talk about the cosmic microwave background radiation. So now let's go through. So I'm going to talk about expansion. Now this is going to be in note form as well, because I think you're pretty good at this. So the evidence is red shift, which is the idea of galaxies, or let's put that in there, almost, oh my god, almost all, and I've got to change that from a capital, otherwise you'll shout at me, almost all galaxies are red shifted. This is like I'm going to try and just squeeze every single key marking point that was in the mark scheme we've just scanned. This is like the Doppler effect for sound. So galaxies are moving further away, so the wavelength is increased due to them being stretched by space-time. Okay, so that's the basics. Now we're going to revisit redshift now, because the idea of them being at a single point is that, and when we look at all the galaxies, they are, the further away they are, the more redshifted they are. And I could put this into the expansion bit as well, but I really don't fancy writing 20,000 bits. Now I'll do the redshift at the end for the single point. I'm going to do the cosmic background radiation. So cosmic microwave, sorry, this is the idea of single point. So now let's go through the single point idea. And evidence for this is the cosmic microwave background radiation can be observed in all directions. Oh, my pen's on a go slow. So cosmic microwave background radiation can be observed in all directions. So the next thing we want to talk about is, well, what is this? So we can say that this came around due to a cooling after the Big Bang. So the microwaves are what we observe due to X-rays being produced by a very hot explosion, and then I'm going to squeeze as much as I can into this, and then after 300,000 years of cooling, atoms forming. Next thing I want to say, because let's get as many of these points in so that you just cover a mark scheme every time, because I've scanned a few and the mark schemes are interesting sometimes in terms of what you need to say for the marks. So now we're going to put in the idea that it's a homogeneous or homogeneous, if Oliver's listening, temperature. So we can observe a from the Big Bang, and that's going to cover us. Now I'm going to put redshift in here with the basic idea of what Hubble told us. So Hubble's law shows the furthest galaxies have the greatest redshift, as they are moving away at a greater velocity. This suggests a tiny, hot, dense initial starting point. Take some practice to get that sorted, and I think that'll do for that. I'm going to just pause that there because I need to go to the toilet.